Hi everyone, welcome to our last lesson on work and energy. Today we will begin by covering the law of conservation of energy. So let's get started. All right, so in science class so far, you have probably learned about the law of conservation of mass, which says that mass cannot be created nor destroyed. This is something you probably talked about in chemistry. In physics, you learned about the law of conservation of momentum, which says that linear momentum cannot be created nor destroyed. And here we are learning about the law of conservation of energy, which, as you can imagine, says that energy cannot be created nor destroyed. And this is, of course, talking about an isolated system where the net force acting externally on the system is zero. So here is a good example of the law of conservation of energy given from this. I took this from the physics classroom, which is a nice website that talks a lot about this stuff. And we have a skier who's starting right here at the top of a slope, and we're told that her kinetic energy is zero right here, and we can assume from that the speed is zero, right? If her kinetic energy is zero, she's not moving, but perhaps she leans forward slightly and starts to accelerate downward, and she will do that because she has potential energy, and she's above some equilibrium position in a gravitational field, right? We're assuming she's on Earth here, so she's right 100 meters up actually. So anywho, she has 50,000 joules of potential energy stored within her up here on this hill. And as she begins to accelerate down the hill, her potential energy is transferring into kinetic energy, right? She's speeding up and she's getting closer to the Earth. So her potential energy is going down and her kinetic energy is going up. And then as she gets to this point here, she has some potential energy still because she's above that equilibrium position, but she is has gained kinetic energy because she's still speeding up compared to this point down here. So as she takes off this ramp, she's now 60 meters above the ground. So her potential energy has grown since this point down here, and her kinetic energy has gotten less. So her total energy is transferring between, again, from potential to kinetic. From here to here, it's going from kinetic to potential. And then she comes down, lands on the ground here where her height is zero, so potential energy is zero, and all of her energy is in the form of kinetic. So she has 50,000 joules of kinetic energy. So the thing that's really important about this diagram here is that the total energy that she has, the total energy that this girl has throughout this entire situation is 50,000 joules, and it's just trading off between kinetic and potential as she moves through the system. So you can see here that her energy has been conserved. Now, it's always true that energy is conserved, right? Energy is, there's a finite amount of energy in the universe, and that is the same number no matter what. It's not created nor destroyed. It simply moves between different forms. So we can categorize energy in two ways. We can say energy is mechanical or non-mechanical. Non-mechanical energy is things like thermal energy or chemical energy, nuclear energy. That's stuff that you maybe talk about in chemistry class, at least thermal energy and chemical energy. But in this class, which is mechanics, we are going to talk about mechanical energy. So mechanical energy comes in two forms. There's kinetic and potential. Kinetic energy is given by that equation 1/2 mv squared. We've learned that already. And potential energy has two forms, gravitational, mgh, and elastic, 1/2 kx squared. So kinetic, gravitational potential energy, and elastic potential energy are all forms of mechanical energy. So the mechanical energy of a system is that total amount of energy all added up together. So there's a special type of systems which follow conservation of mechanical energy, and I want to talk about those systems because that's really what we're going to be focused on for the remainder of this unit. And what this comes down to is analyzing the forces that are active on the object and knowing whether or not they are conservative or non-conservative forces. So a conservative force is a force where the work done on an object is independent of the path taken. So for example, let's say I lift an object straight up. So I take my calculator and I lift it up 2 meters. There is some gravitational force acting on the calculator. If I drop it, right, it's going to be pulled down towards Earth. There's some gravitational potential energy stored within it as I hold it up 2 meters above its original location. Now, let's say I go back to the original location with my calculator And now I lift it up, again, a vertical displacement of 2 meters, but now I've like taken this weird curvy path where I'm like spinning in circles, and I'm going to the left a little bit, and then I'm going fast upward, and then I'm stopping at a 2 meter vertical displacement. The gravitational force on the calculator is exactly the same from both my situations, when I lifted it straight up and when I took a sort of funky path. Right? The energy associated with it, stored within it, is still mgh. It's just dependent on height. And what that really means is that the gravitational force is independent of the path that calculator took. So this is a conservative force. This is what defines a conservative force. The path taken doesn't change the force acting on it. Now, if you think about something like friction, it really does depend on the path that's taken. Imagine if I took my calculator and I put it at the top of a ramp, and the ramp was, just a piece of plywood lying at some angle, and it slid down that plywood. There's going to be friction acting against that calculator as it slides down. But if that plywood was, instead of being a flat piece of plywood moving straight down, imagine it had some curves to it, and it took a turn, or maybe it did a loop-de-loop, or it went up and then went down, and it wasn't a straight path. If it didn't go straight down, there's going to be more friction acting on it in like the curved path, because there's a longer distance that it has to travel to get to the bottom. And in that case, there's more friction acting on it. So friction is non-conservative. It does depend on the path taken. Now, if you have a system where it's only conservative forces, which is called an ideal system, then the mechanical energy of the system is conserved. Another way of saying that is, in the absence of friction, mechanical energy is conserved. And I just want to point out here that, friction exists, right? It exists in many forms. There's air resistance and drag, and, your standard kinetic friction when something's moving across a not perfect surface. And when I say the absence of friction, what I mean is that friction is negligible in many situations, that it's so small that it really doesn't change your answer. So when friction is negligible, mechanical energy is conserved. Now, when you have a system that does have friction, there is a conversion of mechanical energy into thermal energy, right? Heat. That's why you can use friction to warm up your hands on a cold day. You can rub them together, because friction takes mechanical energy and converts it into thermal energy, which is non-mechanical form. So if there is no friction in the system, the mechanical energy is constant. So energy will just change between kinetic and potential for ideal systems. So this situation here that I'm about to show you is a PhET simulation, and PhET might be something that you've heard of before. It's a really great program that shows you some simulations of physical situations. So in this situation, we have a skateboarder and we have a skate ramp. And if I take her and I stick her at the top of this skateboard ramp, she is going to have a lot of potential energy. And when I release her, her potential energy will decrease and her kinetic energy will increase as she speeds up towards the bottom. And then all kinetic energy down here, she has inertia, so she'll keep moving. Her kinetic energy will transfer into potential until she gets up to that height she was at before. Actually, let's go ahead and look at the energy bars here. I'm going to drop her from the top, and you can watch her kinetic energy and potential energy trade off. But you'll see that the purple bar, the total energy, remains constant. Now, this is an ideal system. This is one without friction. But if you know anything about skate parks, you probably know that there is friction, right? So let's make the situation a little more realistic. I'm going to toggle some friction in there. You can see that there's a friction button right here. And what I want you to look at is what happens to the energy bars when I add friction. So you can see now that there is a conversion from her mechanical energy, so kinetic and potential, into thermal energy. And she's eventually going to come to rest at the bottom of the hill, and all of the energy will have finally been converted completely into thermal. So if you were to take your hands and you were to touch the surface of this skate ramp or the ball bearings in her wheels, you might feel some heat instantly after the situation because of the thermal energy. All right, so I want you to think about this problem here. We have a cart below that starts at rest from position A, and the cart is shown at several locations along the path. I want you to rank the following from greatest to least. So tell me the most potential energy to the least, and then tell me the most kinetic energy to the least and the most mechanical energy to the least. So potential energy is given by the equation mgh. So the height above the equilibrium spot, or whatever you call as your reference point, which would be the bottom here, is going to determine the potential energy. So the higher up they are, the more potential energy. So from greatest to least potential energy is going to be A, C, and then B and D are the same. Kinetic energy is going to be the opposite of that. Objects speed up as they move towards Earth, so the closer they are to the ground, the faster they're moving. And in this situation, we're looking at something that's ideal. So there is no friction acting in this situation here, which means that the kinetic energy is greatest at B and D, then C, and then A. And lastly is the mechanical energy. Now, because the system is ideal, the mechanical energy remains constant. So the mechanical energy at A is equal to the mechanical energy at B, which is equal to the mechanical energy at C, which is equal to the mechanical energy at D. Now, before we move on, I guess I should mention that roller coasters are kind of a classic example of conservation of mechanical energy laws, because they really are frictionless or nearly frictionless. If you've ever been on a roller coaster, what happens is that you get into this cart, and then you put your seatbelt on and all that, and then there's a chain link connected to a motor that links to the bottom of your car, and then it cranks you up to the top of this hill. So like the motor does work on the cart to get you to the top of the hill. And so you have a bunch of energy stored within you because that motor did work on you, or the cart. And so now you have stored potential energy within you. And roller coasters are built to be nearly frictionless. The first hill is going to be the largest hill. It's where all of your energy comes from throughout this whole thing, is the potential energy that the motor did to get you up there. And then you're released and you start to go through all these different obstacles, maybe a loop-de-loop, maybe you go upside down. But the entire time you're on that roller coaster, you are transferring your energy between kinetic and potential with very little loss due to friction. And then at the end of your roller coaster, what will generally happen is you'll hit a spring, and that spring will compress until you come to rest, and then you'll lock into place, and the spring will be released on the other end, so the energy will come out on the other end. But this is like the general way that roller coasters work. So it's important to note here that as we look at roller coasters, you should assume that they are frictionless and ideal. All right, so let's try one that is a little more complicated. We have a person on a roller coaster cart. They're 65 kilograms. They start at rest on the top of a frictionless hill, which I've marked in green as position A. They roll down the hill to the bottom, that's position B, and then move through a loop-de-loop at position C, and finally come to rest by compressing a spring at the very bottom of the hill. I want you to find the speed at position B, find their speed at position C, find how far the spring is compressed at D. And you'll notice if you look at this diagram that I've gave you a lot of known values. I've given you the height at A and C. I've given you the speed at A, they're at rest, and I've given you the spring constant at position D. So go ahead and see if you can solve this problem, and it might help to find the total mechanical energy of the system first. All right, so first thing I should note is that the mechanical energy at position A is equal to the mechanical energy at position B, which is equal to the mechanical energy at position C, which is equal to the mechanical energy at position D. And now it might be worth it to just write out the equation for the mechanical energy at each of these points. So the mechanical energy at A is equal to it's only potential because the cart is not moving, so it's just mgh at A. The mechanical energy at position B is only kinetic because it is at the bottom of the ramp. The mechanical energy at C is above the bottom of the ramp, so there is potential. And it's also moving, so there's also kinetic. And then lastly, at position D, the mechanical energy is all elastic potential because it has come to rest after it hit the spring and compressed it. So 1/2 kx squared. So my first part is to find the speed at position B. So what I can do is I can set the mechanical energy equations here and here equal to each other. So mgh at A equals 1/2 mvb squared. Now mass can cancel because it's on both sides, right? I just multiply everything by 1/m. Right, I'll do that. And then, so I have gh equals 1/2 times vb squared. So now I can multiply everything by 2. And now take the square root. So if I am going to solve for the speed, it's the square root of 2 times 9.8 times the height at A was 23. It's 21 meters per second. That's the speed at location B, the bottom of the ramp. All right, now I'm looking for the speed at position C. So let's set the mechanical energy at A equal to the mechanical energy at C. So we have mgh at A, that's the potential energy, right? Which is all of the energies in the form of potential at position A. So mgh equals at C, we have potential and kinetic. So it's going to be the sum of these two. Now mass, I'm going to multiply everything by 1/m to get rid of my mass. So I have GHA equals GHC plus 1/2 BC squared. And I'm trying to isolate this guy, so I should subtract GHC from both sides. Now multiply everything by 2 and take the square root. Now I can plug in. The height at C was 12. I'm going to do this piece by piece because there's kind of a lot here. So 9.81 times 23 is 225. And then 9.81 times 12. So 225.63 minus our answer gives us 2 times 107.91. This was a square root, so this is going to be square root. So multiply that by 2 and then take the square root of that answer. And I get 15 meters per second. Part C, our final part here, is asking us how far the spring is compressed. So I am going to set the mechanical energy at any location, but I'm just going to pick A again, equal to the mechanical energy at D. So I have mgh A equal to 1/2 kx squared. Now I cannot cancel m because m is not on the side of the equation. So my m is not in every term. So instead I'll just go ahead and isolate x. So let me get rid of, wait, is that what the question was? Yeah, how far is it compressed? So that's x. So I'm going to multiply everything by 2. And then divide everything by k. And now take the square root of everything. That's going to be 2 times, our mass was 65, times 9.81. The height at A was 23. And then I'm dividing that by K, which was 840. times 840, or divided by 840. So I get 5.9 meters. Last thing we're going to learn about today is power. Power is the rate at which work is done, or more generally, power is the rate at which energy is transferred by any method. Right? If work is the transfer of energy, then power is the rate at which energy is transferred. The units for power is the watt, which is represented as a capital W. So if you ever have heard of something measured in watts or kilowatts, that is a value for power. So like a 60 watt incandescent light bulb, that is a power rating. Now, the equation for power is work over time, right? That's the way to mathematically express the sentences above it, right? Work over time. And there's an alternate form of the power equation that is very useful, which I'll derive right now. All right, so starting with our equation for power, we have power is work over time, and we know that work is a force multiplied by, we know that work is a force multiplied by displacement. So if this is true, then I can insert this expression here into the top of that fraction for power, right? Because force times displacement is equal to work. So I get power equals force multiplied by delta x over delta t. And now I can see that this expression here, delta x over delta t, that's average velocity. So power is equal to force multiplied by velocity. And, power is actually a scalar. And really what you would do to find power is you'd multiply the force times the speed. So you'll often see this written as power is force multiplied by speed. All right, and our very last problem for the day will be this. It takes me 45 minutes to push a mower, a total distance of 600 meters. I pushed with a force of 180 newtons at an angle of 45 degrees. How much power did I use? So my time is 45 minutes, which I do want to put into seconds because seconds is my SI unit. The distance traveled for this thing is 600 meters. I push with a force of 180 newtons at an angle theta of 45 degrees. Now power is going to be force times speed, and it's also work over time. So I can actually use either, and maybe I'll do both to show a little comparison, but I just want to point out that if I'm using this equation, it's the component of the force that's parallel to the displacement, right? So if I'm using this, I would find power by multiplying 180 cosine of 45 times 600 over whatever that value is in seconds would be my speed. Anyways, let's first use just our regular equation that we learned first, the power is work over time. So work is going to be force multiplied by delta x times cosine theta, and that's going to be over time. I should convert 45 minutes into seconds too. So 45 times 60 gives me 2,700. So we have 180 times 600 times the cosine of 45 and divide that by 2,700. I got 28 watts. And let's see if using the other method I get the same thing. So power is the force parallel times the speed. Now speed is distance over time, 600 over 2,700 is 0.22 meters per second. And my forced parallel is 180 cosine of 45. So 127 newtons. So my 127 newtons multiplied by 0.22 repeating gives me 28 watts. So both work to give you the same answer. And, I'm thinking you probably noticed this as I was going through it, that when I'm multiplying f times speed, speed is distance over time. And so 180 cosine of 45 times 600 is the same thing as that, right? Divided by 2700. So I should, of course, get the same answer. Thank you guys so much for watching. I will see you all in this week's class.